Hello everyone, this is Meng Cho from Kyushu Institute of Technology, Japan. It is my pleasure to give KiboCUBE Academy online lecture about CubeSat mission assurance. First, let me introduce myself. I have been working at the Kyushu Institute of Technology, QTech, in short, since 1996. Originally, my research area was spacecraft charging or spacecraft environment interaction. But nowadays, I'm more interested in lean satellite, which are another way of saying a small satellite. These are the pictures. These are pictures of the satellite where I have been the principal investigator. Since 2012, so far 23 satellites have been launched into space. QTech is a national university founded in 1909, which has a history of more than 110 years. The university has 3 campuses focused on science and technologies. We are located at the Kita-Kyushu region, which is 1,000 kilometers west from Tokyo. In terms of distance, the distance to Korea is much shorter than the distance to Tokyo. At the QTech, I have been the director of the Center for Nanosatellite Testing. Since 2010, we are capable of doing all the tests for a satellite up to 50 centimeters, 50 kilograms. We open test facilities to external users who are looking at the place to test their satellite. So far, we have tested more than 70 satellites, including satellites from the overseas, such as Egypt, Costa Rica, Singapore, Malaysia, Vietnam, and Thailand, and others. So in March 2022, the center received a Space Development Utilization Award, JAXA President Award, in recognition of contribution to the space sector. At the QTech, we are not only testing satellite, we also build satellite by ourselves. These are the satellites I have been involved with until now. We have launched 25 satellites since 2012. 7 more satellites are in the pipeline and will be launched after 2024. According to Bryce Space Technology Report on small satellite by number, Bryce Tech is a consulting company located in US. QTech has launched more small satellites than any other academic institutions in the world since 2012. Now let's move to the lectures. The purpose of today's lecture is to introduce how to assure the mission success of CubeSat projects. We focus more on university projects, but many of the contents also apply to CubeSat projects developed in startup company. This is the content of today. After the introductions, I'll talk the root causes of the failures we investigated. Based on the root cause analysis, a mission assurance handbook was published recently. In the third part of this lecture, I'll extensively talk about the contents of the handbook. First, let me introduce a university satellite project in Japan. In Japan, many universities who carry out satellite projects belong to the University Space Engineering Consortium, UNISEC, in short. UNISEC now has local chapters worldwide as UNISEC Global. UNISEC Japan consists of 36 university and research institutions, 49 organizations, 636 student members, and 262 individuals and 19 corporate members and alumni members, based on these statistics of April 13, 2021. So UNISEC Japan members maintain cooperative relationships in conducting practical space development and utilization. This shows satellite developed by UNISEC Japan members, UNISEC Japan member universities up to 2019. So we have more in the past 3 years. So there are more than 50 satellites developed and operating. So in 2020, due to pandemic, we had a lot of free time, not being able to go to work or even travel. So members of UNISEC Japan came up with the idea of using free time for something productive. So we had the remote sessions on lessons learned from University Satellite Project in UNISEC. During the remote sessions, more than 20 professors talked about the lessons learned from their own project. Everybody talked very honestly about what really went wrong and how they could prevent it, and but failed to do so. How they implemented the lessons to the next project, and so on. It was really a good way of using the free time during the pandemic. Later that year, we talked with JAXA about these lessons learned activities. JAXA said it is a very good activity and offered some sponsorship to promote activity further. With the JAXA sponsorship, we did a survey on the lessons learned in terms of mission assurance and made a report made of 439 pages on analysis about the success and failure cases of domestic micro and non-satellite projects and their causes, and extractions of a requirement for mission assurance on micro and non-satellite. Unfortunately, this document is in Japanese, but nowadays there are many good translation software on the internet, so you can use that. So following the activity in 2020, in 2021, UNISEC members worked on a mission assurance handbook for university-based lean satellite. We did further analysis of the failure cause by intensive interviews with persons in charge of each project. Based on these activities, the mission assurance handbook for the university-built lean satellite was published in March 2022. This lecture will present some of key components found in the handbook. The first chapter in introductions to small satellite in general. This table shows the summary of lessons learned. We investigated in detail. The more detail of each case is available at the KiboCUBE Academy Session 2 on demand pre-recorded lectures. Please scan the QR code here to access the video. There are 8 cases shown here. The satellite we investigate range from 1U CubeSat to 50 kg CubeSat, 50 kg satellite, which are obviously not CubeSat, but they were built by university teams and can be categorized as lean satellites. We interviewed a key person of each satellite project to analyze the root causes. We found many common causes among different cases. They are poor schedule management, team structures, inconsistency in requirements, improper verification plannings, wrong strategy to avoid total satellite loss, insufficient full system end-to-end test, difficulty in assembly, integration, and testing, poor understandings of the rationales behind the design, and others. Based on this analysis, the mission assurance handbook was made. Now let me talk about the mission assurance. Mission assurance is defined as a series of activities to identify the factors in design, making, operation of the satellite and others that will hinder mission success and to eliminate or decrease the effect of such factors. At the same time, we should consider that most university satellites are categorized as lean satellite. A lean satellite is a satellite that utilizes non-traditional risk-taking, development and management approach with the aim to provide satellite value to the customers and or stakeholders at a low cost and with a short time to realize satellite missions. For more details, you can see the reference listed below. Lean satellite tolerate risk but still need to achieve mission success as much as possible. So it is not failure is not options, but it's not failure is accepted. based on the lessons learned activity, the root and the root cause analysis, we have developed the Mission Assurance Handbook for the university-built LEAN satellite. It is targeted at the satellite project at the universities and polytechnic colleges in Japan. It covers not only the first project of the university, but also the second and the later project. The handbook lists a summary of points to be kept in mind of faculty members and students to improve the mission success rate. It is organized in the order of project life cycles. The book is already published. The first version was already published in 2022, and the second version was published in 2023 March. Although the handbook is targeted at the Japanese universities, much of the content is still applicable to satellite projects in new space company or non-Japanese organizations. Therefore, English versions has been made as well. So to download the latest version of the handbook, please use your smartphone and capture the QR code below. Yes, it can be freely downloaded. These are the contents of the handbook: introductions, project management, mission definition, conceptual design, detailed design, productions, testings, operations, post-operations, sustainability of a university satellite project. Chapters from 3 to 9 are in the order of project life cycles, and I will now introduce some of the contents. So from now on, please note that the page titles numbers are the ones used for the mission assurance handbook. So the number it changes now. So 2.1, chapter 2.1, project management. So in this chapter of the project management, we write about the schedule management. It is a fact that first project often fail. Mostly, it is due to improper schedule management, coming from the lack of satellite project experience. Because of this, very little time is spent in the system test. In this chapter, we write a guideline for the project milestones until satellite delivery. In this table, D is a satellite delivery. So at the 13 months before the delivery, the proof of concept should be obtained. The team should confirm that the missions are feasible with more solid evidence, such as breadboard models testings, than a simple analysis on paper. Usually, a preliminary design review is held at this time. How long it will take to reach this D-13 months milestones depends on what the mission is to be done. The simpler the mission is, the shorter we can expect the time to be. And it is important to have the courage to give up some missions if the feasibility is uncertain at this time. For procurement of engineering models, components should start by D-13 months, 10 months before the delivery, and all EM hardware components are supposed to be delivered and ready for the system assembly. So 10 months before delivery, everything, although it is EM version, engineering model version, it must be on the table. For some components, it takes more than 3 months to be delivered. So procurement of such components should start earlier than this D-13 months. While you are waiting for components to come, don't relax. There are many things to do, such as structure analysis, STM vibration test, and software analysis, using BBM. So you also need to secure the test facility for engineering models testing during this period if you do not have the testing facilities readily available. The assembly, integration, and testing of EM is 4 months. You are supposed to verify interface compatibility from the component delivered. A significant amount of time is spent in troubleshooting. You also learn testings. For the first satellite, EM vibration test will not be completed in one test. I have seen many projects, including ours, doing many vibration tests at the EM stage. Don't do many vibration tests in FM stage because it accumulates fatigue in the structure, but for EM vibration test, yes, you can. And certainly at the first test, you cannot finish because students are not experienced. The more tests the team does, the more experience they obtain. The time spent in each test will become shorter because of the learning curve. 6 months before the delivery, the engineering model testing is finished. The satellite functionality should be confirmed as a system. Usually, a critical design review (CDR) is held at this time. 3 months should be spent to procure all the flight models hardware. Based on the EM testing result, some design change may become necessary to move to FM. I think in a university project, no change from EM to FM is very rare. Yes, you have to have some changes. You have to improve the design, but it's okay. As long as it is minor, you can move. So in principle, so there should be no design change, but yes, it's unavoidable. Because the CDR is confirmed that design is okay, but yes. So because design change may occur, you have to allocate enough time from the transition from FM to EM phase. Because it usually takes an unexpected amount of time. When FM components are delivered, you need to do functional checks one by one. There is no guarantee that FM works just because EM works. I have seen many of these cases. Yes, so don't assume because EM works, FM will work. So you have to test. So you also need to secure the test facility for the FM. Although the test facility are secured, you may be forced to change the schedules due to unexpected delay in FM assembly and integrations. So make a schedule margins so that once you secure the test facility, make reservations. And if you have to skip, change the reservations, don't assume the test facilities are always available. Test facilities are usually packed with many test requests. So you have to have a certain margin. Also, if you cannot have that test facility, you also need to make plan B about where to test. 3 months before the satellite delivery, all FM hardware components must be delivered and ready for FM system assembly. This means that the satellite assembly, integrations, and testings is finished in 2 months. It's very intensive, yes, but it can be done. And the repair of the FM may be necessary if defects are found. The test schedules may change day by day, so therefore the team members must make their schedules as flexible as possible. So you have to have allocate your own time for this satellite project. Yes, students are busy for testings. Students busy for their exam and lectures. But yes, when they have to work, they have to work. Yes. So 1 month before the delivery, flight model hardware and software should be complete. Hardware testing, such as thermal vacuums, vibrations, others, should be finished by this time. Basic ground station software is complete. The final months before delivery should be spent in final verification of the flight software by doing long-duration system end-to-end test using satellite flight model. It's important to use flight models in the ground station. You may find bugs in the flight software. You need to judge whether the bug is actually fixed or not. Because if you think you fix a bug, you may introduce another bug if you replace the flight software. So you have to be very careful about the risk of changing flight software at this stage. Especially if you cannot update software one after satellite goes to orbit. Most of the university satellite does not have such a capability. So the flight software you install cannot be changed. So be careful when you change flight software. So another important aspect of project management in terms of mission assurance is team talent. It is not possible to have all the talent necessary for the project by students alone. The team needs to find solutions to fill the gap. One is to procurement, i.e. solved by money. Two, collaboration with external people such as amateur radio expert for the case of communications, or we can expect students to grow. Even for one or two, the requirement for the procured or outsourced items must be made by the team, not by the vendors or the collaborators, because the university team is responsible for the upstream system requirement, and also they are the ones who do the system test. Another important thing specific to university project is to keep the persons familiar with the satellite design for operation. This is a unique problem for university project because students graduate when the time comes to operate the satellite. To keep personnel, the teams needs to finish the project life cycles from kickoff to operations in 3 years. Because in typical Japanese universities, students stay in the laboratory for 3 years, from the whole 3 years of undergraduate to the end of master course. Finally, the principal investigators, which is very often a faculty member, i.e. a professor, should be responsible for keeping students motivated. I think that's probably the most important job of professors. Also, the professor should be responsible for securing the communications channels for external assistance. Because the student does not know what to ask and is afraid of making a contact to a big professor in other universities. So if you're a professor, don't just say to your student, oh, contact professor in this universities. He knows everything. No, you have to first send at least one email to that professor saying that this person, this student of my teams want to ask questions. I'm not capable to answer the questions, so could you please assist us sparing some of your time to answer the questions? I would appreciate very much, something like that. So you should send some email, you means a professor, send some email. Then the students or junior members can ask. Yes. Remember, when you are a student, you are afraid of asking questions to a big professor. So in the project management of university satellite project, lean philosophy is important. Satellite project activities are categorized into 3 activities. One is a value-adding activity. such as improve satellite reliability, enhance attitude control accuracies, and others. 2 is non-value added but necessary activity, such as safety compliance, frequency license, Space Activity Act compliance. There are pure waste, such as searching for tools. So lean philosophy tries to eliminate the waste and do the non-value added but necessary activities efficiently. When we look at university satellite project, we can see many waste in moving and waiting. To eliminate the waste, having the office, the workrooms, the testing rooms, and the ground station in one buildings is desirable. You may argue that when we are moving for the inside campus for the meetings, we are thinking about a satellite project. Well, some students, or you may be doing, but most of the students are just looking at the smartphones and reading text. Yes, so those moving is really the waste. So if you multiply 5 minutes by 10 member, it means 50 minutes of time wasted in the moving. So in the satellite project, frequency coordinations and radio license applications are very important. The mistakes in those may result in a change of satellite design, change of satellite missions, delay of satellite delivery, giving up satellite missions, limit on satellite operations, and others. We often see that the work related to the frequency coordinations and the radio license concentrate on specific members. We need to consider human natures. A person can understand the work is necessary, and we can convince one member to be in charge of a task, saying, yes, this is very important. But often a person doesn't work until the deadline approaches. You may well remember when you are a student, or if you are a student now, I understand that you don't start studying just until the night before your exam, right? So although person understands a deadline, he or she doesn't start until really necessary. So it is recommended that multiple members, including PI and project managers, monitor progress and routinely check and motivate the persons in charge of frequency issues. This is about safety requirement verifications. Everybody should understand that non-compliance with the safety requirement may lead to serious delays of the schedules. In the worst case, the satellite is not launched and the dummy mass goes to space instead of your satellite. This picture is a proof of that cases. This shows dummy mass, which was actually launched because CubeSat was supposed to be launched at this slot, but they couldn't comply with the safety requirement. So at the last minute, it was switched to the dummy mass. So it is recommended to list up the issues related to safety requirement and confirm with the launch provider at the end of conceptual design as well at the end of detailed design. The safety requirement verifications, this verification of safety requirement is important, and how to verify is agreed with the launch provider. But when you agree, you should agree on the method that can be done with a minimum effort. It should be noted that safety verification is necessary, but it is a non-value added activity. Therefore, spend minimum time in safety verification and do more value adding activities such as mission assurance. For documentations, why do we need document? Everybody says documents are necessary in a satellite project. Why do we need document? They are needed because of the regulatory work, communication with the project, within the project, traceability for the anomaly failure investigations during the operations, knowledge transfer, sharing knowledge and know-how with other projects, to write a journal paper or thesis. For mission assurance, the point B, C, and D are important. They are important for anomaly and failure investigations during operations and to reflect the lessons learned to the next project. We need to understand, however, the fact that very few students likes making documents. I wish I could see such a student, but unfortunately I haven't seen such a student. Therefore, the faculty members or the staff have to think about how to encourage students to write the document. One idea is to link this activity with the students' bachelor or master thesis. Then they have to write a document anyway to graduate. But in this case, although we have documents which are very detailed in a specific subsystem of the satellite, we cannot have a comprehensive set of documents covering the entire project. So perhaps you have to let the project managers to write a master thesis based on the project. So in the mission definition phase, mission feasibilities should be thoroughly checked. You should know the limit of team talents, skills, and the budget when you define the missions. Also, important, professor is not the goal. You should keep it in your mind. A professor doesn't know everything to judge the mission feasibility. Professor should have open mind to suggestions, comment, assistance by others. For example, when you are building the first satellite as a team, if the mission requires 3-axis stabilizations and pointings, I strongly recommend to modify the mission. Also, if high-speed communication is necessary for a project done by students of mechanical department, its feasibility is extremely low. The success criteria are the guidelines to make progress in the project. The success criteria are usually composed of 3 elements. The first one is minimum success, which is things to be achieved even if the satellite has problems. The second one is full success, which is things to be achieved when the satellite works as expected. The third one is extra success, which is something more than expected in addition to the full success. You should use quantitative indicators as much as possible, especially for minimums and full success. You may need to change the criteria as the project proceeds, but every time you need to examine whether the meaning of the entire project can be achieved. You should ask questions to yourself. Can we satisfy the project stakeholders? When you discuss a design change, you need to examine whether the minimum success criteria can be achieved. When you make the operation plan, you need to try to achieve the minimum success criteria as soon as the satellite is deployed into orbit. You should keep in mind that anything can happen in space. Therefore, the first priority is to achieve the mission success criteria. The first priority is to achieve the minimum success criteria first. For what mission will be done in orbit, the operations scenario of each mission, called also as a concept of operation, should be made. For each mission, we need to consider the sequence of command from the ground station, functional flow inside the satellite, downlink to the ground stations. This mission scenario is useful for function analysis to derive the design requirement. You also need to make budget tables regarding communications, power, attitude, or pointing. The budget tables does not have to be very precise at the beginning, but it needs to be revised as the project goes on and improves accuracy. If the mission has no margin at the mission definition phase, that mission is not possible. So you have to think again. You need a margin. Right? Just barely satisfying the budget is not good enough. So how much budget, how much margin you need? I think that's based on experience. So you have to ask somebody who has experience outside of your team. So in the conceptual design phase, requirement management is done. You need to check consistencies between the mission requirement and the design requirement. Design should satisfy the mission requirement. If there is a design requirement that doesn't fit to the mission requirement, then there is something wrong. One example is the case of this satellite. It used an experimental patch antenna for communications, although the mission was education. So it's really contradictory. So the satellite should have used a very robust design antenna. To avoid the inconsistency in the requirement, external review by experienced expert is effective. So similar to the margins I explained in the previous page, external reviews at the mission conceptual design phase or mission definition phase are really helpful. Yes, because you have to admit you don't have experience. Then you can ask for help from outside. Yes. So don't hesitate asking help. So it is also important that teams, especially principal investigator, should have open mind to external suggestions. Yes, I think that PI, the attitude of PI is also very important. In the conceptual design phase, a verification plan should be made. A design should not be used if it cannot be verified. Also, the verification should be doable. To have a doable verification plan, first list up the minimum test items and put priorities. This is a table to list minimum test requirement for ISS, International Space Station, released CubeSat. Priority should be given to this test item marked as required in this table. In a detailed design phase, you start selecting parts and components. There are various reasons to choose a particular vendors for each part and component. But you should not decide the vendor by price and performance only. It is better to consider also availability, easiness of handling, meaning clear interface, good response to repairs or questions. These points are sometimes more important than size, price, functionalities. For the second or later satellite, the same component without any new development work should be used to minimize the development work. You should understand the slight changes may lead to cost increase or longer delivery time. So even if a student says, yes, I want to change this capacitors and this patterns of the circuit to this way, you really have to ask a student, you mean the PI or program manager, the project managers, have to ask why this change is necessary. Is it really critical to do the missions? If not so critical, just keep the older design, and that worked. Okay. If it didn't work, yes, you have a good reason to change. Anyway, even slight change of patterns or change of parts may cost a lot. So you have to think the consequence of changing the design. Also, in the long run, it is better to think of developing components jointly with a vendor, aiming at transferring all the know-how to the vendors in the near future. Because you cannot maintain the know-how and skills inside the university. By transferring those to a company, you can have a sustainable supply chain of the component. In the detailed design phase, our risk management, FTA and FMEA are done. FTA is fault tree analysis. FMEA is a fault mode effect analysis. The important thing is try to minimize the risks based on priority, because in university satellite project, there is no resource to deal with all the risk items. External review is effective, again, to list up the risks with high priority along with the safety issues. FTA and FMEA are often said to be important. Yes, they are important, I understand, but we should understand also that FTA, FMEA are not taught. We do not teach in school for most of the cases. Therefore, you should start FTA, FMEA from the levels student, professor can understand. So you list up single point of failure and prioritize the risk. When you do this, not only part component, but also works. Long command, long assembly, and others should be considered. Because human errors are very likely in university project where many members are just beginners. The satellite should be designed so that it can avoid the complete failure under any circumstances. The complete failure means the loss of communication with the ground. There are various tips for die-hard satellite. God PIC or microcontroller PIC 16F877 for power reset. Battery can be recharged even if it is completely depleted. Satellite works without a battery using solar panel only. Redundant communication links if you have enough volume. Feasible power budget to be able to communicate with the ground stations even if satellite loses attitude controls. The satellite fails in solar panel deployment. Satellite loses one solar panel. If you implement a power reset design, many university satellite does, you need to verify that the satellite can recover from the power reset. Sometimes satellite can enter a so-called zombie state after the power reset because there could be many leakage current inside the power. So even if you think you reset, you turn off the microcontroller, you are not. And after you are turning on the main switch, those microcontroller is still at the hanging state. So you have to be careful. So in that case, you have to have some time gap from the turn off to turn on, so that all the leakage current and capacitors, everything is depleted. So you need to make sure that won't happen. So when you change the design, you should evaluate the benefit obtained by design change and the new risk generated by the design change. So you always talk what is the benefit, what is the risk. This shows one example. Antennas and radios. Antennas and radios have no flight heritage. We want to improve the reliability of communication. Then the design in the left was proposed so that we can change the communication, a combination of radio and antenna using this RF switch. So even if one is, so they can serve each other as a redundant. However, there is a risk of the RF switch becoming stuck in an intermediate position, which means no communication at all. So without RF switch, communication is still possible if we do this version, even if one pair of radios and antenna survive. If one pair of radio and antenna survives, it's okay. So you should consider a design and that makes a satellite operation easy when you design a satellite. Yes. First, imagine how to execute the mission. Also, reflect the lessons learned from the previous operations. Stored command or reserved command is useful. It makes mission executions possible anywhere in the orbit. It can do a series of maneuvers. You can increase the amount of data by downlink to ground stations other than Japan's. In your case, yes. Although you need to declare that in frequency coordinations. In ITU document, if you don't say that we downlink in this country, you cannot do because that country must agree on that radio is coming from that satellite. Simple uplink commands are desired because small number of bytes improve the uplink success rate. It is good if ground station software can adapt remote and automatic operations because the team size may be significantly smaller during operation due to gradation. The satellite should keep housekeeping data history before power reset. The satellite should keep important parameters before after reset. One important parameter is control gain of attitude controls. Otherwise, every time after reset, you have to uplink those parameters again. Satellite design should make the satellite easy to assemble, integrate, and test. You should reduce the number of fasteners, bolts, screws, harness, connectors as much as possible. They are a very strong possible cause of workmanship errors. Human makes mistakes. You should implement mitigation designs against mistake in design. One example is that this PCB has a cut in the corner to identify which side is from. Because the connector at the bottom must be placed at the front side. Student often makes mistakes the side and solder the connect in the wrong direction, wrong side. So just saying being careful is not the solution. You should have the connectors. If you attach and remove, you should save the connector. If you attach and remove the connector frequently, it may damage the connector. External ports to internal processors are needed so that you can program and debug components even if the satellite is fully assembled. Physical inhibit against antenna deployment are needed for the case of piggyback satellite. You may want to work on software until the last minute before satellite delivery, but deployment may not be allowed after the final safety review. So you better have, so if your design says as once a satellite is activated, antenna deployment is automatic, it's very difficult to work on software. So you have to implement something. You should prepare jigs for the assembly, test, storage, like the one shown in later pictures. Yes. You also need to think about how to carry a satellite. Please don't carry satellite by your hands, especially by one hand. Yes, please never carry hand. Use two hands. Okay. So in the satellite production phase, quality controls becomes necessary. University satellites use commercially off-the-shelf components. It's called COTS extensively. Quality of COTS parts are guaranteed by the manufacturers as mass-produced items. If an anomaly occurs, it's most likely it's due to improper handlings after delivery. Therefore, the mitigation against static electricity is necessary. Always make yourself grounded. Grounded means your body has the same electrical potentials to the ground. Yes. If not, you may be charged, especially during the winter, and once you hit the PCB, printed circuit board, if there is voltage difference, you may ignite a spark. That spark may kill electronics parts. Also, you need to handle the parts in a clean environment. It should be noted that individual COTS parts, its quality may be guaranteed, but the quality of component is not necessarily guaranteed. I mean, individual DC-DC converters or the oscillators, capacitors, yes, they are guaranteed. But once they are assembled, it's not really guaranteed. So university satellite components are often one of a kind, so there is no established manufacturing process in the component vendor. So even if multiple components are made simultaneously, there is no guarantee that all the items are good. So what you need is once a component is delivered, a basic functional test shall be done before it is integrated into the system. In a production phase, you may debate whether we should have the manufacturing work outsourced or do everything in-house. You should understand the purpose of an educational satellite is to make a student practice systems engineering and project management, not acquire handyman skills. You should not try to save money by making a satellite in-house. After all, it may end up in schedule delays and cost increases. Some students have very good hand skills. I admire those students. Yes, some are very good. Especially I have very poor hand skills. But many students do not have hand skills. It's even worse than my hand skills. Relying on student hand skill is very risky. So for very important ones, you should ask professionals to make. So one example which I often do is that connectors, harness with a connector. we always ask professionals, because when student makes a connector, it's very loose sometimes. So in every step of satellite production, compliance with safety requirement has to be verified. Verifications of safety requirement in FM stage is very critical to pass the safety review. You need to agree on safety hazard control method with the launch provider before FM assembly. Then you need to verify that control method were properly implemented according to the agreement. Before moving to FM assembly, the team members, especially AIT team, assembly integration testing team, should be aware of what procedure they have to follow and what document they need to make. Otherwise, at the last minute, this kind of meaningless fight occurs inside the team. Yes, it often occurs, yes. Good communications between safety officers and AIT teams is necessary. In the testing phase, electromagnetic compatibility EMC test is important. Because of the cold launching requirement, EMC with launchers and other satellites are not important. Then what we need to verify is whether the satellite can live with its own self-generated noise. We need to verify that communication link has enough margin. Uplink signal levels should be much higher than the satellite-generated noise flows. This must be confirmed before moving to FM. Because if the noise floor is too high, many design changes, such as antenna, component layout, and others may become necessary. In the testing phase, the mission feasibility must be verified in an end-to-end manner. As early as possible during the satellite development phase, you need to verify the basic data flow of the main mission. It is made of the following: command uplink, satellite does its missions, such as image capture, yes, and data is downlinked, and confirmation of data on ground station PC. After confirming that the basic mission can be done in this manner, you can make the detail of the mission. This confirmation should always be done once you move to EMS or FM phase. Even if the component works alone, there is no guarantee that it works in the system. Before integrating the component into the satellite structures, you should verify the interface with other satellite components. You should note that even if it was okay in EM, it is not guaranteed that FM is okay. So this is the case of the combining all interfacing of the component. Yes, especially if the components are coming from different vendors, interface is really the nightmare. So you should be careful. In the testing phase, a system function test is extremely important. You need to move to FM assembly as soon as FM components are delivered and start the function test as an integrated system. Even if all the components haven't arrived yet, you should from the component available. In functional test, you need to check the consistency of the data sent from the satellite, not just confirming that the data came, look at the content, You need to look at the content of the data. So don't be satisfied if you see some hex data in the computer screen. You have to convert to physical data, and that physical data must make sense. If you are downloading image must appear on PC. If you are downlinking housekeeping data such as voltage value must appear. If there are problems, you should not move to the environment test, such as vibration or thermal vacuum, before you solve it. You should expect many problems to be found once you assemble FM, and so you need to have enough schedule margins before moving to the environment test. For examples, do not expect that you can start thermal vacuums in 1 week after you assemble satellite for the first time. I think many university projects have such a very short, tight schedule. No, I think 1 week is not enough. End-to-end long-term operation test is done for 3 purposes. One is to find and fix bugs of flight software. 2 is to do operation rehearsals. You need to do critical mode, release, recovery from reset, and others. Nominal mode, housekeeping data collections, mission mode. These 3 are to confirm the link budget and compatibility with the ground station. In the link budget, line loss and the noise levels inside the satellite here. It's hard to derive theoretically because satellites are too densely packed. You need to confirm the link budget by testing. This test must be done by using actual individual flight models, and the line loss and noise levels may differ depending on each satellite. Deployment tests are critical considering the fact that 25% of university satellites end up DOA, dead on arrival. One suspect is antenna deployment. They fail in antenna deployment. You need to make sure that the antenna can be deployed even in the worst case, which is a cold and low battery case. When you use a heat cutter, you should have enough margin in the time you heat up the nickel wire. CubeSat may not fit into the pod at satellite delivery. If this happens, it is really a nightmare. The best and the simplest way to avoid is to do fit check with the official pod borrowed from the launch provider. The reason for saying officials is that a slight difference in the pod size makes a result very different. So this must be official. I have seen many times CubeSat fits into one pod but not in another type. The fit check should be done both for the EM and FM. CubeSat, especially the big one, the 3U, it's skewed when you assemble with a real PCB inside. And the tolerance is really limited, 0.1 millimeter. So there are often really possible that it doesn't fit to the satellite. Thermal vacuum test is a thermal vacuum test. So the satellite size doesn't matter. Even if you have very big satellite or small satellite, it's the same. But one note here is about temperature conditions in the thermal vacuum test. You have to define high and low temperatures. For large satellites, the conditions is derived by the thermal analysis and thermal balance state. Yes, you have to do. But for CubeSat, there are many flight data already available. After all, more than 2,000 CubeSats have already flown into orbit until today. Then using flight data of similar satellite flown in the same orbit is much more accurate than using thermal analysis result. Especially many CubeSats have flown already in ISS orbit. The surface property made of solar panels and satellite mass are more or less the same. Then I suggest to use flight data obtained by other satellite. This is one example. We put the on-orbit data collected by the bird satellite. Yes, in this link, you can check. Then it should be noted that you should use high beta angle data for high temperatures, as eclipse time is very short or so. When you evaluate the test, you should be very careful. Often mistakes in test setup or procedure are overlooked. You need to check the consistency of the test result. The pass-fail criteria should be established before the test. If the result deviates from the tolerance limit, you need to try to explain why. If something hard to understand occurs randomly, you need to record the observation. Don't be optimistic and you have to fight against normalcy bias, such as perhaps it won't happen in orbit. It was just a random noise. We just saw illusions. Let's forget about it. So you should confirm that the test equipment is used properly. Very often, students make mistakes of using, especially RF equipment, radio equipment, because they don't have enough experience of using them. Right? It's very rare that a student have experience of using spectrum analyzers or vector network analyzers. Yes. The test setup needs to be checked by multiple people. Concerning the operations, the ground station should be prepared, considering maintenance and access. Satellite operation can be performed anytime in a day, or unless you launch a satellite to some synchronous orbit. Therefore, access to the ground stations at midnight is very important, and access to the antenna for maintenance must be easy and safe. During the operation phase, maintenance of antenna pointings is necessary. You often observe that uplink success rate decreases. Then you may want to suspect that antenna pointings had some errors. The easiest way of knowing the antenna pointing issue is to track a known satellite, such as ISS. This is a picture of an antenna, which is broken. Yes, in this case, somebody has to climb up. By the way, this antenna is a top floor of 8-story buildings, so it's not wise for students to climb up. It's too dangerous. So we have to call professional. Yes. And if we have to repair 2 or 3 times a year, actually we do, because there are lots of hurricanes, it costs some money. So you have to do something that makes this one easy to maintain. So in one antenna we have some elevator, so we can just lower the antenna so that we can access to the antenna even if we do not climb up this antenna tower. So when you align the antenna, do not use a compass to find the north, because the magnetic north is different from geographic north. It's somewhere in Greenland, not in North Pole. If we look at this antenna pattern, what typical UHF Yagi antenna used for the ground station, a 10-degree error in the pointings causes significant error. So you need to find some landmark located at the north by looking at the Google map. Nowadays you have Google map, it's very easy. And point toward that one. Okay. Google map north is geographical north, it's not magnetic north. Okay. When you do operations, you need to put priority on obtaining the frequency license as soon as possible. Because at the time of launch in Japan, you have only a preliminary license obtained before launch. You need a full license to operate a satellite officially and publish the result. Even if you have a very good result, you cannot publish the result without full radio license. So in Japan, the full radio license is issued after confirming the two-way communications, downlink and uplink is established. Also, you need to do the main mission first. You try to achieve the minimum success criteria as soon as possible, because satellite can be dead anytime. The satellite reliability decreases quickly at the beginning of operations, known as first infant mortalities. Many satellites fail in the first several weeks. For the first satellite, you may be excited by hearing the satellite beacon, but you need to move to the main missions before anything can happen to the satellite. Anything can happen in space. So please remember. The satellite may go wrong at any time, but the team should never give up, even in such cases. There are the satellites that recovered after 2 years without communication. Yes, it's real. Yes, yeah, there are such satellites. It is important to maintain motivations within the team. What is the most important is the positive attitude of the professors, the principal investigator. Even if the satellite fails completely, it is important to identify the cause to reflect the lessons learned to the next satellite. When the main mission becomes impossible to achieve, if the main mission becomes impossible to achieve, but the communication is still possible, it is important to continue acquiring the on-orbit data as much as possible, because the lessons learned in operations can be reflected to the next satellite. When you do the fault tree analysis, FTA, it is recommended to do this along the information flow. It is recommended to investigate whether problems occur within a block of within each block or at each interface of blocks along the information flow from the ground stations to the satellite, from the satellite to the ground station. The flight spare on the ground is quite useful to do the FTA. So whether the problem is in the ground station or not can be easily checked using flight spare and the ground station equipment. Yes, here. The problem in the satellite is investigated by checking the possible cause of failure. The observed event should be listed first. Using the flight spare, experiment to replicate the observed event should be done. To do FTA, the most helpful is the members who actually develop the satellite. It is strongly desired that the project schedules is established so that members engaged in the development remain in the team during satellite operation. Once a satellite deorbit, the operation is finished, but there are still things to do. Lessons learned meetings by the team members, documentations, know-how sharings with the next project or other university teams. To do the know-how sharings, the information should be in a suitable state. You can't just exchange the raw data, so you have to make a data so that readable by others. So you need to process the data in a way other people can understand. Even if you fail one satellite project, you can succeed in the next project. You need to constantly improve satellite design, AIT, operation, and management. Then you should build a series of satellite projects as a satellite program. How to accumulate lessons, knowledge, and know-how obtained should be considered carefully. It is good if persons with actual experience of the project life cycles continue to serve in the next project. This cannot be done by students because they graduate. The lessons learned should be inherited by the professors or staff. If it is done by the professor continues to engage in satellite project as a program director. If it is done by research staff or young faculty members, they need to get involved in the programs for a long time. There must be a system that the junior researchers can build up their academic careers. To continue other programs, funding is needed. It depends on effort by individual professors. There are no miracles. Money won't come from heaven. You have to do something. University satellite projects are often run as a laboratory project of each professor. To run the satellite project as a programs, support from the university management is really needed. To get the support, contribution to the universities is necessary. You need to give something to universities. Then you get something from universities. Well, it is like a contract with the devils, but the decision is yours. Yes. The support may be limited if there is no value other than advertisement of the schools. You can add education aspect in terms of engineering design, project-based learning, or a practical study of systems engineering. Continuous support may be obtained if the satellite program is a part of educational curriculums, because school management cannot say no to the educational curriculum. But even in this case, the amount is limited. Anyway, you shouldn't expect much financial support from the university unless you belong to very rich university. So when you think of expanding satellite programs in the universities, coordinations with other professors cannot be avoided. It is to take the satellite project from a project of a Professor A to a programs of Professor A, B, C, and more. Collaborations between the engineering faculties and the science faculty is a good idea if there is a science faculty in the campus. Collaboration between a laboratory to make a satellite and laboratory to use the satellite data, such as AI, IoTs, and others, is also a good idea. Finally, conclusion. University CubeSat project can take a risk, but we still need mission success. It is not failure is not option, but neither is it failure is accepted. The second version of the Mission Assurance Handbook for university-based Lean Satellite is now available. Lean Satellite adopts a risk-taking, non-traditional approach toward low-cost and fast satellite buildings and operation. University CubeSats categorized as lean satellite. The handbook summarizes the point to be kept in mind by faculty members and students to improve the mission success rate. Many of them apply to non-Japanese universities and new space companies. That is why I gave this lecture today. The handbook is open to comments by the lean satellite community worldwide to improve the mission success rate of university satellite. So your comments are highly welcome. Thank you very much.